Hello everyone. Today I'm very glad to talk about our recent work, zinc oxide thin film transistors for large area sensing systems, preventing process-induced dielectric breakdown. Our systems are featured with using large area electronics. Let's first talk about why do we want large area electronics. Large area electronics basically means that we have thin film transistors on flexible and large area substrates. They are processed at low temperature, which is usually less than 200 degrees, which benefits for its large area and low cost, and also enables many applications, sensors, actuators, display, and so on. But the challenge in large area electronics is that thin film transistors usually have low performance. So from the comparison table, we can see that thin film transistors, no matter made of amorphous silicons, organic materials, or metal oxides, usually have macron channel length and megahertz cutoff frequency, which has way worse performance compared with crystalline silicon CMOS. So our approach to deal with drawbacks of the thin film transistors is to use hybrid systems, basically combining large area electronics and silicon CMOS. Large area for sensing and silicon CMOS for readout and computation. However, one challenge of such hybrid system is the large number of interfaces because of the large number of distributed sensors between LAE and CMOS. These connections are usually very fragile and we don't want this. Our approach is to build TFT-based interfacing circuits on large area electronics for interface reduction. This work, we are motivated to explore large area electronics in such hybrid systems. For form-fitting distributed sensing, our system is basically TFT-based compressed sensing circuits for interface reduction in tactile sensing. However, for fabricating such a system, there are several challenges, which this work is for. The first challenge is long metal traces in such distributed sensing systems. These long metal traces are like antennas. They are very vulnerable to damages. Second one is plasma processing. From the TFT cross-section we put it here, we can see that the aluminum oxide, zinc oxide, and aluminum oxide are dielectric, channel, and passivation. They are all deposited with plasma-enhanced atomic layer deposition. The plasma could cause damage. The last one is packaging and assembly damage because we are making hybrid systems. Let's first take a look at our system we built. This system is to use TFT-based compressed sensing circuits to reduce the number of the interfaces to CMOS IC. Basically, what happened is that the currents from the sensor array go to our compressed sensing circuits, effectively as a matrix projection to the sensor currents. The readout unit reads out the compressed data, and then we do a reconstruction algorithm to reconstruct the data. And finally, we get 98% accuracy. So the interface reduction is successfully demonstrated. The first problem to make such a system we have is get dielectric breakdown during process. The IV curve showing here is after fabrication. We can see 10 thin film transistors overlaying together with transfer curves, but they have very divergent curves and 30% transistors are get shorted. Also, for diode, we have 161 TFT circuit per die. The diode with all 161 TFTs functional is 2 out of 98, very low. Why does this happen? In this work, we modeled the damaging mechanism, validated it, prevent the damage in experiments. Let's first look at the top view of part of a circuit. We can see that the gate metal of the lithium transistors are connected to a very long metal traces. In plasma processing, we look at these long metal traces. When they are looked in a PALD chamber, because of the non-uniform plasma we assume, the surface of sample will be charged differently at different locations. The long gate lines basically serve as a current path. Plus, the substrate is isolated. There will be current turning through the depositing oxide, as shown in the figure. This tunneling will make the oxide break down. For prevent this to happen, we then isolated the TFT gates for the long metal traces and do all of our fabrication. After the TFTs are made, we reconnected them with the top metal layer. Finally, after this, we see huge improvements of IV curves. First, the curves are much more uniform and there is no gate short. And the diode for all 161 TFTs functional increases to 40 out of 77. That's the first problem. Another problem is about gate dielectric breakdown during dicing. We can see that before dicing, there are 40 circuits with all 161 TFTs functional per circuit on glass. But after dicing, no functional circuit is left. And we also tried to cover the sample with top and bottom metal shields. But this only increases dicing yield slightly to 3 out of 20. We thought about what could cause this problem, and we developed a capacitance imbalance breakdown model. Let's take a look at the model. C1 to C4 are the capacitance between top or back metal shells and source drain or gate. From the circuit model here, if the ratio of the capacitances C1 over C3 versus C2 over C4 are not equal, there will be voltage on the gate dielectric C5. Actually, if all the capacitors are all ideal planar capacitors, the ratios were equal, but in the real world, they are not. So the ratios are not equal and the voltage on the gate dielectric will build up. Then, with these simulations, we found that if there is no pinhole on the photoresist, there will be about 9 volts built up on gate dielectric, not enough for it to break down. However, if there is photoresist pinhole, about 80 volts will be developed, far enough for breakdown. Our approach in this work to prevent this damage to happen is to use shorting bars to short all the gates to their source drains after die test before dicing, so the voltage on the dielectric during dicing is kept almost 0 volts. The shorting bars are removed by lithography and etching after dicing. By doing this, from the comparison table, we can see that the dicing yield is increased from 0 out of 40, 3 out of 20, to 5 out of 5. To summarize, in this work, we prevented plasma damage, improved the die yield from 2 out of 98 to 40 out of 97 by isolation between TFT gates and long gate lines. We also prevented dicing electrostatic damage, improved the dicing yield from 3 out of 20 to 5 out of 5 by shorting bars. This enables successful demonstration of compressed sensing and reconstruction in tactile sensing with 98% accuracy. Thank you very much for listening.